So in this video, we'll take a peek under the hood of hash functions, and I'll discuss some of the high-level principles by which they are implemented. So let's briefly review the raison d'etre of a hash table. So the purpose in life for a hash table is to support super fast lookups. So maybe you're keeping track of the transactions that happened on your website yesterday. Maybe you're keeping track of your employees. Maybe you're keeping track of IP addresses in an internet router. Maybe you're keeping track of chess configurations in a chess playing program, whatever. The point is you want to be able to insert stuff into a hash table and later remember whether something's there or whether something's not there. So the implementations we'll discuss will generally also support deletions. But that's pretty much it. It's a very restricted set of operations, but the hash table is going to execute them very, very well. So basically in constant time, again, subject to some fine print, which we'll discuss a little bit in this video, but then more deeply in a separate optional video. So the two caveats are, first of all, the hash table better be properly implemented. It's actually pretty easy to screw up a hash table, to screw up hash functions. We'll talk a bit about that in a few minutes. And then also, the data should in some sense be non-pathological, and that will be discussed more deeply in a separate video. All right, so let me give you an initial glimpse of some of the magic that's happening under the hood in hash functions. So first let me say exactly what the setup is. The first step is to identify all the things that you might want to be storing. So in other words, the universe of your application. So this would be something like all possible IP addresses, of which there's 2 to the 32. All possible names you might encounter, perhaps with a maximum of, say, 30 characters. All possible configurations of a chessboard, and so on. And one thing I hope you can appreciate from these examples is that in many cases this universe is really big. So the number of IP addresses is quote-unquote only 2 to the 32. The number of all names, you're probably talking more like 26 raised to the 30. All chessboard configurations I don't even want to think about. And what you want to accomplish is you want to maintain an evolving subset of this universe U. So maybe you want to keep track of all the IP addresses you've seen on your website in the last 24 hours. You want to keep track of the phone numbers of all of your friends. You want to keep track of the chessboard configurations that you've explored in the past 3 seconds, whatever. And again, what I hope is clear from the applications we've been discussing is that this set S is usually of reasonable size. It's something you could store in main memory. Maybe it's tens of thousands of IP addresses. Maybe it's, a few hundred names of your various friends. Maybe it's in the, millions of chessboard configurations, but still way, way, way smaller than the size of the universe. So without data structures, you'd have to resort to rather unsatisfactory solutions to maintaining this set. So the first thing you could try, as we discussed in the previous video, would be you just have an array with one position for every imaginable thing you might want to store in your set. So this is the solution that's going to work well if all of your friends happen to have names that are integers between 1 and 10,000, but doesn't scale when the universe size becomes really big, as in most of these applications. So the good news is of course it's an array and it supports fast random access, so you can access any position in constant time. So if you have an array-based solution indexed by all the elements of your universe, you can do constant time insert, delete, and lookup. The bad news is the space requirement is proportional to the universe. And again, forget about being unsatisfactory. That's just literally impossible, infeasible in many applications in which you'd use hash tables. Now, of course, to get the memory proportional to the size of the set stuff that you're storing, an easy solution would just be to use a list, say a doubly linked list, something like that. Now, with a list-based solution, the good news is your memory is certainly proportional to the size of the set that you're storing, and it's independent of the size of the universe from which these elements are drawn. The bad news is to figure out whether something is or is not in a list, you generally have to traverse through most of that list, and so that's going to take time proportional to the length of the list. So really the question we're faced in implementing a hash table is, can we get the best of both worlds of these two naive solutions? On the one hand, we want to have the constant time operations enjoyed by the array-based solution, but on the other hand, we want to have the linear space and the size of the set that we're storing that we get in the list-based solution. So to get the best of both worlds, we are going to use an array-based solution, but the array will not be big. It will not be with size proportional to the universe. The array will only have size, roughly the same as the set that we're storing, so somewhere in the ballpark of the cardinality of S. So the first thing we do is we decide on how big we want our array to be. So that length is going to be called n. We're going to have an array of length n. And n is going to be in the ballpark of the size of S. It's going to depend on a few things, exactly how n compares to S, but for now think of n as like double the size of S. We're going to be calling each entry of the array a bucket. So there's n buckets, and then the size of S is about 50% of the number of buckets, let's say. So one objection you might legitimately raise at this point is, I thought I said the set was dynamic, the set S, right? Stuff can be added, stuff can be deleted. So the size isn't always the same. It can fluctuate over time. So what does it mean to define an array which is roughly the same length of this changing set? So for simplicity, for the purposes of this video, to focus on the key points, I'm going to assume that the set size S, while S itself can be changing, I'm going to assume that the size of S doesn't fluctuate too much. So there are additional bells and whistles you can add to a hash table implementation, and they're all quite natural. I think most of you could probably figure them out on your own to deal with the fact that S might be changing sizes. So for example, you can just keep track of how many elements are in your hash table, and when it exceeds a certain threshold, so when it's too big relative to the size of your array, you just double the array, and then you reinsert all of the elements into this new doubled array. Similarly, if you want to, if the set shrinks, you can have tricks for shrinking the array dynamically as well. So I'm not going to discuss these bells and whistles for resizing your hash table dynamically. They are, of course, important for a real implementation, and they are part of the implementations in the standard programming libraries. But I view those as sort of a second order point in the implementation of a hash table, and I want to focus on the first order points in this video. So summarizing, think of the set S. There are insertions and deletions we have to accommodate, but S is going to be roughly the same size, and the number of buckets will be within a constant factor of the size of the set. All right, so now we have our array with totally reasonable space proportional to the size of the set that we're storing. And now what we want is some way of translating between the things we care about, say our friends' names or whatever the elements of the universe are, to the positions in this array. So the object responsible for that translation from keys drawn from this universe to positions in this array is called a hash function. So formally, a hash function takes as input a key, so this is going to be an IP address or the name of somebody or a chessboard configuration or whatever, and it's going to spit out a position in this array. So I'm going to label the array entries from 0 to n-1 for this lecture. Obviously at the moment this is super underspecified. There's a zillion functions you could choose. Which one do you use? We'll talk about that, but for now there's just going to be some hash function mapping from elements of the universe to buckets, to positions in this array. Now, as far as the semantics of this hash function, what the hash function is doing is telling us in which position we should store a given key from the universe. So if we have some new friend named Alice, and we run Alice through the key Alice through the hash function, and it gives us a 17, it says we should store Alice's phone number in position 17 of the array. If we have some crazy chessboard configuration, we feed it into a hash function and it spits out 172. It says we should remember this chessboard configuration in the 172nd bucket of this array. So again, given x, which is some key from this universe, we invoke the hash function to get a position in this array, to get a bucket, and that is where we try to store this x and any associated data with it. So that's the high-level idea of how you implement a hash table, but we're quite far from done. And in particular, there's a serious issue that we're going to have to deal with that's fundamental to implementing hash tables, and that's the notion of a collision. So probably many of you have already noticed that this problem might occur, which is, well, what happens if we're storing our friends' phone numbers and Alice shows up and we ask our hash function where to store Alice's phone number, and it says, oh, bucket number 17. And then our friend Bob shows up and we ask our hash function where to store Bob's phone number. And what if the hash function also says bucket number 17 for Bob? What do we put in bucket 17? Do we put Alice there? Do we put Bob there? Do we put them both there? How do we deal with these so-called collisions? So the next quiz is meant to get you thinking about collisions and in some sense how unavoidable they truly are. All right, so the correct answer to this question is the first answer, believe it or not. All you need is 23 people in a room before you're equally likely to have two people with the same birthday as not. So if you're looking to skim a little money off of your non-mathematical friends, this is one way you can do it. Go to cocktail parties with about 40 people and place bets with people that there are two people in the room with the same birthday. So if you have 367 people, well, there's only 366 distinct birthdays. I'm counting February 29th here as one of them. So by the pigeonhole principle, certainly the probability is 100% by the time you get to 367. Now, by the time you're at 57, you're already at 99%. So you already have overwhelming probability to have a duplicate birthday with 57 people. So of course with 184, you're going to be almost at 100%, 99.99 Who knows? Some large number of 9s. And at 23, you're at 50%. So many people find this quite counterintuitive, that you only need 23 people to get a duplicate birthday on average. All right, so this is a quite famous example, and it sometimes goes by the birthday paradox. Calling it a paradox is sort of a misnomer. Paradox, often suggests some kind of logical inconsistency. There's no logical inconsistency here. It's just that people's brains are not really wired to have this intuition for whatever reason. But it's really just math. You can work out the math and you can just solve it. So more generally, the principle behind the birthday paradox is the following. So suppose you have a calendar, perhaps on some different planet, which has k days, where everybody's equally likely to have each of the k days as their birthday. Then it's about the square root of k people that you need in a room before you're equally likely to have a duplicate or not have a duplicate. And the reason that you get the square root effect is because if you think about it, there's a quadratic number of pairs of people in the room. So that's a quadratic in the number of people opportunities to have a duplicate, right? So each pair of people could be a duplicate. There's a quadratic number of pairs, and so that's why once the number of pairs starts reaching about the number of different days, you're going to likely see a duplicate around that point. So you might be wondering why I'm telling you about the birthday paradox in the middle of a lecture about hashing, but really it's quite relevant. So imagine, for example, you defined a hash function in the following way. Now, to be clear, this is not a practical hash function, but just for the purposes of discussion, imagine you have a hash function which randomly assigned every single key to a uniform bucket. Okay, so for each of the 1 over n buckets equally likely, then what the birthday paradox says is, even for a very small data set, you're already going to have a pair of things colliding, right? So if you have n buckets, so maybe n is like 10,000, all you need is roughly 100 elements in your data set, and despite the fact that the table is only going to be 1% full, you're already going to see a collision. Okay, so 99% of them are empty, but you're going to have one bucket that has 2. So that's sort of annoying. So the birthday paradox says you start getting collisions with a hash function, even with really tiny data sets. So in this sense, if you're going to have hash tables, you got to deal with collisions. There's going to be a fair number of them, and you need some method for resolving them. So collisions are a fact of life when you're talking about hashing. Where again, by collision, what I mean is two different keys, so two different elements, x and y, from the universe that hash to the same bucket, who have the same hash value. So in general, we can think of a hash function as doing a compression of sorts. So we have a huge universe U, and we have this very modest size array A with only n buckets, where n we're thinking of as being much, much, much smaller than U. So, of course, this hash function has to map various elements of U to the same bucket. So what are we going to do about it? How are we going to resolve these collisions? Well, there's two different solutions which are both quite prevalent in practice. So solution number one is called chaining, or sometimes you'll also see it called separate chaining. And this is a very natural solution. It's also the one that's relatively easy to analyze mathematically. What you do is just for elements that hash to the same bucket, you just revert to the list-based solution that we talked about in a previous slide. So each of the n buckets will not necessarily contain just merely 0 or 1 elements. It will contain a list with an in principle unbounded number of elements. Okay, so when we use chaining, it's then quite straightforward to figure out how to implement all of the hash table operations, namely insert, delete, and lookup. You just hash something to the appropriate bucket, and then you just do insert, delete, or lookup as appropriate in the list that's in that bucket. So just to make clear that everything is type checking, so here h of x, this is the bucket for x. That's what's specified by the hash function. And then in the h of x position of this array A, in the h of x bucket, is where we find the linked list that is going to contain x. So just to give a cartoon example, if you had, say, 4 buckets, maybe the first bucket has exactly 1 record corresponding to Alice. Maybe the second bucket just has a null pointer. No one's been inserted into the second bucket. Into the third bucket, we have, let's say, both Bob as well as Daniel. And then maybe in the fourth bucket, we have Carol. Okay, so because we have a collision between Bob and Daniel, both map to the third bucket, and we resolve that just by having a linked list with Bob and Daniel in some order. So the second solution, which is trickier to talk about mathematically, but still quite important practically, is called open addressing. And the principle in open addressing is you're not going to use any space for pointers. You're not going to have lists. So you're only going to have one object per bucket of the array. So now the question is, what happens if you try and insert Daniel and you invoke the hash function on Daniel and it takes you to a bucket that already contains Bob? That means there's no room for Daniel. So what you're going to do is you're going to probe the hash table in some other position. So a hash function is now going to be replaced by a hash sequence, where the hash function tells you the first bucket to try to insert Daniel, failing that, a second bucket in which to try to insert Daniel, failing that, a third bucket to try to insert Daniel, and so on. And you just keep trying until you find an open position somewhere in the array. So there's various strategies for trying to figure out the probe sequence. One strategy is if you fail in, say, bucket number 17, which is where the hash function tells you to go first, you just try bucket number 18, then 19, then 20, then 21, and so on, until you find your first open slot. So that's called linear probing. And another approach is double hashing. So this is a solution where you actually have two hash functions, hash function number 1 and hash function number 2. And the idea is, suppose you're trying to insert, say, Daniel into a hash table with open addressing, and you evaluate both of the hash functions. And the first one comes up 17, and the second one comes up 23. So as usual, the first hash function will specify where you look first. So if it evaluates on Daniel to 17, you look in the 17th position of the array. And if it's empty, that's where you insert Daniel. Now, if it's full, what you do is you use the second hash value to be an additive shift. So unlike linear probing, where after 17 you look at 18, with double hashing, if the second hash function gives you 23, that's going to be your offset. So after 17 you look at bucket 40. If 40 is already full, you look at bucket 63. If bucket 63 is already full, then you look at bucket 86. So you keep adding increments of 23 until you finally find a bucket where that's empty, and that's where you insert Daniel. Now, of course, if you try to insert some other name, if you try to insert Elizabeth, you're going to get two totally different numbers in general. So maybe you'll get 42 and 27. And so here the probe sequence will be 42, failing that, 69, failing that, 96, failing that, 123, and so on. So a question you should have at this point is, I've told you two solutions to resolving collisions in a hash table, and you're probably asking, well, which one should you use if you have to implement your own hash table? And as usual, if I present you with two different solutions for the same problem, you can probably rest assured that neither one dominates the other, right? Otherwise, I wouldn't waste your time by presenting both of them to you. So sometimes chaining is going to perform better, and sometimes open addressing is going to perform better. And of course, it also depends on what kind of metric that you care about. So there are a couple rules of thumb that I can tell you. So first of all, if space is at a real premium, you might want to consider open addressing instead of chaining. And that's because with chaining, you do have this extra, it's not huge, but you have a little bit of space overhead in dealing with all these pointers and these linked lists. So if you want to avoid that, you might want to think about open addressing. The second rule of thumb is deletion is trickier with open addressing than with chaining. Right? Deletion is clearly not difficult at all, either to code or to understand when you use chaining, because it just reduces the deletion from a linked list, which of course you all know how to do. Open addressing it's not impossible to implement deletion, but it's much trickier. So if deletion is a crucial operation for you, that might skew you toward thinking about chaining. But ultimately, if it's really kind of mission critical code, probably the best thing to do is implement both kinds of solutions and just see which one works better. It's a little hard to predict how they're going to interact with memory hierarchies and that kind of thing. They're both useful in their own contexts. All right, so we've covered the two most prevalent ways of handling collisions, and we argued that collisions are inevitable. No matter how you design your hash function, you're stuck with collisions, and you can do chaining a linked list per bucket, or you can do open addressing, where you actually have a probe sequence in order in which you look at buckets until you find an empty one. And the elephant in the room at this point is, what is this hash function? I've told you nothing about hash functions. All I told you is that there's some mapping from the set of universe, so IP addresses or names or whatever, to a bucket number. What kind of function should you use? Excellent question. Tons of research on that question, and to this day, as much art as science. But let's start talking about it.